Hey guys, in this video we're going to be learning about what are called complex circuits. So to begin with, we need a definition of complex circuits as opposed to simple circuits. So there's really two basic varieties of complex circuits. There's ones that have multiple batteries, okay, which are wired in parallel. Or they contain perhaps connections which are properly considered neither series nor parallel. So an example of the first case can be seen below. For something like this, you can't actually talk about, quote, I total, because the total current in any particular branch comes from possibly more than one place, nor can you talk about the equivalent resistance. So neither of those concepts that we've used previously to help us solve circuits will apply to a complex circuit. Similarly here, in this example of the second case, we can't determine the equivalent resistance because there's a connection here in the middle which really can't really be considered to be series or parallel exactly. An even crazier example, which I encountered this problem the other day on the internet, but I swear I did it in college, is where you have a cube of resistors arranged. And that's getting into extra wild territory. I will not give you one where we have a cube of resistors. On the other hand, we will actually do this one. Right, now, so if we can't use the concept of equivalent resistance and total current to resolve all of the currents in this circuit, what tools do we have left to us? Well, the answer is Kirchhoff. Back when I introduced Kirchhoff's laws to you, I said we can use these two laws to analyze any circuit. Two laws, any circuit. And that's true for complex circuits as well. But we have a little bit more that we have to learn about some sign conventions, given that in this circumstance we have some less conventional wiring arrangements. So first convention is this. If you are following a loop and it goes through a battery, meaning some particular direction, okay? Let's say at first we're going to do following it in the direction that the battery would normally push current. That is, from minus to plus. The battery gives you positive volts. But if you are instead drawing a loop which happens to go against a battery's natural polarity from plus to minus, you actually lose volts. So meaning when you write your loop equation, instead of doing something like 12 minus IR, or whatever, you might get negative 12 instead of that positive 12 if it's a 12-volt battery and you are following your loop in a direction which is against that normal natural polarity of the battery. All right, now there's a similar thing going on when we get to resistors, but resistors are a little more tricky. With a battery, the battery doesn't care which way the current's actually flowing, and believe it or not, current can sometimes flow against a battery. That would be what's known as charging a battery. Actually happens all the time. But okay, regardless, if the current is flowing in this case I drew it in the upwards direction, and the loop that you are following goes with the direction of the current, then you get what you're used to seeing in all of your loop equations, which is the resistor is using volts. But if the current is going, let's say, up the page, and you are drawing a loop which goes against the current in that particular resistor, notice you're going to have plus IR for that one. So meaning in your loop equation, you could easily have something that goes like EMF minus I1 R1, okay, whatever, and then plus I2 R2 equals 0, whatever, okay? So you can have minuses or pluses in front of the term for a resistor, just like you can have a minus or plus in front of the term for a battery, depending on the direction that you follow the loop relative to either the battery polarity or the direction that the current is, the direction that you said the current was flowing. So all of those rules and sign conventions that I just said are very nice, and they make perfect sense to me saying them out loud. But I think they really, really need to be demonstrated in an example. So this one right here could be example 13 in your notes packet. I've changed some of the numbers, but the setup is identical except for the numbers. So you could work it out there. if you're looking for space. The first step in analyzing any circuit, or especially a complex circuit, is to draw the currents. Normally I'd ask you to pause at this point and draw them in, but I'm just going to go ahead and start things off by drawing in a current. And there we have a current. Now the direction that I picked for it follows the polarity of the battery. Remember, we said batteries push from minus to plus, and so that is presumably the correct direction for the current to flow. It needs to be stated, though, that you could honestly pick any direction for the currents and still get all of the right answers. We don't have to guess well. We just have to draw in a current. So you must draw a direction for all of the currents. So draw them all in, name them. Now, currents, again, they can flow against a battery. Remember, that corresponds to charging a battery. So if this 12-volt battery were like 120 volts, odds are pretty good that the current in the 6-volt battery would be flowing that way and not this way, the direction that the battery kind of wants the current to go. Because sometimes that's just how it works out. But I would say, as a general rule, as often as possible, draw currents that sort of follow the natural direction that the battery would tend to push, and then write all of your equations corresponding to that. And the only reason for this is because it makes it slightly easier a lot of the time to write your loop equations. All right, so that means the 6-volt battery will be pushing current up, and since this junction right here has two currents coming into it, one from the left and one from the right, probably the current in the middle wire is going to be going in the downwards direction. It would be sort of silly if I said that I2 went up, because we can't have three currents going in and none coming out. That would just be impossible. All right, now the next step I want you to do on your own. This is write a junction equation. A lot of the time, for some reason, people go straight to the loops and want to do everything with loops, and you actually always need at least one junction equation for these kinds of problems. Okay, you always will need a junction with a complex circuit problem. So pause me, write a junction equation, and then resume the video. If you wrote that, well done. Remember, the rule is current in equals current out. So if you just look at the arrows, that'll tell you whether it's going in or out. So it shouldn't be a lot of guesswork there. Now, you'll notice we have 1, 2, 3 unknowns. So if I want to solve for 3 unknowns, I need 3 equations. So I wrote one junction equation. Ta-da! All right, now I need, therefore, 2 loop equations. Just 2. I'm actually going to write 3 loop equations for the sake of demonstrating to you some of the unusual sign conventions that we're trying to practice over here. But we actually only need 2 more equations. So if you've got 3 unknowns, 3 equations. If we had, say, 4 unknown currents, then we would need a 4th equation. Now, the first loop that I'm going to draw, I actually want you to try it out first, because it follows all of the rules that you're used to. So here's the loop that you're going to do. It's going to be this one. So pause me, try it on your own, and then resume. And there you are. That's the loop equation for going like this. And that follows all of the sign conventions that you are used to, right? That's the normal format, right? You've got the battery, minus IR, minus IR. And then that's it. So 3 terms. Now, just for the sake of argument, though, we could have gone through that same exact path in the opposite direction. And let me just demonstrate that real quick, solely for the purpose of practicing our new sign conventions that we've learned. If I instead followed my loop like this, I mean, it's the same path. We're just doing things in, the opposite order and going against the directions of the currents that we drew. And the result is going to be that all of the signs will flip, all of them. So if I go against the 8 ohm resistor, right, go up against it. When I say against it, what I really mean is not against a resistor. That's nonsense. Against the current that I drew, well then, instead of having minus 8I2, I will have plus. That's this sign convention. All right, as I keep on going, now I'm going against I1 through the 10 ohm resistor. So this will be plus. And now, finally, I'm going against the battery. When we say against the battery, we're talking about going opposite its natural polarity from plus to minus, and that's this sign convention. That would be now a negative 12 instead. All right, so it's the exact same equation, just with all the signs switched, which is the same thing. All right, now, I say that because sometimes you will have to write loops that go against currents that you've drawn or other things like that. So this is not a useful new equation, but it demonstrates anyway the new sign conventions. All right, now go ahead and try and write the equation for this loop. Again, this one should be pretty conventional. And there's that one. Again, this is a relatively conventional loop, okay? Nothing weird happened here. We gained 6 volts as we went through the battery, going from minus to plus. The current is going up through the 6 ohm resistor, and I'm following my loop up through it. That's with the current. So I have minus IR, minus 6I3. And then we're going down through the 8 ohm resistor, which is the same direction as what I said for the current, so minus 8I2. All right, so a conventional loop like the ones that we've been used to writing. All right, the last loop is going to be this one. I want you to follow it around the perimeter. You don't have to follow it the direction that I drew. You could go any which way, meaning you could go counterclockwise instead of clockwise. It doesn't matter. But try, to the best of your ability, to write that loop equation, being very conscientious about these rules that we have on the left side of the screen. So pause me, try and write it. Just try it. Now, that loop equation is a little bit funky, right? Because we're using, let's call it an unconventional loop. It's not what you're used to, all right? But it follows the rules that we said to the left. I went up through this battery from minus to plus. So I gain 12 volts. So that's why it's a positive 12. Now I'm following the current through the 10 ohm resistor. When I follow the current through a resistor, that's when I have the minus. All right, and then here I go, keep going around. Oh, now I'm going against the current through the 6 ohm resistor. So thus, this one's a plus instead of a minus. And I'm going against the battery, right? For batteries, it doesn't matter which direction the current is going through them, it's just what's their polarity. So plus to minus, that's not the direction batteries want you to go. So I lose those 6 volts, and then we get back to the beginning without going through any other circuit elements. All right, now between these 4 loops, we have enough to plug in to the Polysimul app on your calculator and solve for those 3 unknown currents. So I'm going to show you. In fact, I have an extra equation. I'm only going to need to use 3 of them. Probably I'll use these 3 right here because those look a little bit simpler to me. And I'm going to look at using Polysimul in the next video because I'm out of time for this one.